Hi everyone, welcome to another Calculus 12 lesson. Today we're doing 1.5, which is rate of change. So we're at the tail end of the chapter. We're basically applying all of the skills that we learned in this chapter to wrap things up. So you'll notice here it says rate of change is one of the most important uses of calculus. And there's a few different ways that it can show up. We've already talked about rate of change in the past. You can see here, rate is equal to change in x over change in y. And we know from before that that is the same thing as slope. So rate of change is slope. So I think it's helpful to look at it in familiar terms, something that you're used to seeing. So there's one way that rate of change can show up. And then there's a couple of other ways that we looked at or that we learned. So the next one here would be average rate of change. And that is where we have the limit as x2 approaches x1 for f of x2 minus f of x1 over x2 minus x1. If you actually look at the details of what this is, all it's saying is the y value, the second y value minus the first y value over the second x value over the first x value. So it's the same thing as slope as well. It's our slope formula that we've been using. It's just, again, from this different limit perspective instead of the x2, x1 stuff that we did before and y2, y1 stuff. And then the last one here is instantaneous rate of change. And that is similar to the stuff that we did last day, which is the limit as h approaches 0 for f of a plus h minus f of a all over this h value. So we practiced and learned sort of the difference between this one here and the difference between this one here. We did that last day. So we get to apply that and get to see some scenarios where this comes up. So rate of change can also be looked at as velocity. So velocity we could say is like rate of movement. And recall from Science 10, Physics 11, Physics 12, you've all seen this before, most likely, where velocity is equal to the change in distance over the change in time. So let's take a look at some examples. And again, you've likely done these types of questions before in a science class, but we're now going to look at it from this perspective, from a calculus perspective. So not a whole lot of new stuff. The only new idea is the limit concept. So in our first example, it says a car is accelerating from a stoplight, has a distance function d of t equals 3t squared. So that's the function that we're working with. And it says what is the average speed over the first 4 seconds. Okay, so if it's over the first 4 seconds, then sort of going back to these equations that we looked at, we can use our x2 can be this 4 seconds that we're told. So I'm going to make that 4 seconds. And if it's the first 4 seconds, then x1 I would assume is starting at 0. So I'm going to make that 0 seconds. Okay, so if that's the case, then if we are looking for our average speed, I'm going to do that here, average speed, that would be our total distance over our total time. So we want to use that formula, this one, the limit as x2 approaches x1 for f of x2 minus f of x1 all over x2 minus x1. I'm going to get rid of that because it's running into there. So, knowing that and applying that, we can start to plug things in. So, in order to figure this out, we can say that our y2 value, when we plug this in, is just going to be from here, we're going to plug in this 4 into this equation. So I'll color code it so you can see what's happening. So basically, in order to fill in like this portion here, let's do this so that we have 3 times 4 squared. And then I'll do this part here. Minus, it would be f of x1. So I'm just going to do the same thing, but I'm plugging in 0 squared. So we can see where that's going to take us to. And then that would be all over this 4 that we got from here. And it would be minus this 0 that we got from there. So to start off with, it's a pretty straightforward one because we're dealing with the first 4 seconds. So to have a value of 0 to work with makes things much easier. So we can see that that's just going to cancel out to give us 0, and we just have a 0 at the bottom, so it's just one simple calculation in order to figure this out. So we end up getting here that our velocity, is equal to 12, and it was meters per second when we work our way through this. Okay, so I hope that that is helpful and pretty straightforward. So it's basically taking this formula from the ones that I listed today and just number crunching and punching things in. But the important part is understanding why you're doing these calculations and where it's coming from. Okay, so then in the next one, it says, what was the speed of the car at t equals 3 seconds? So for this one, I want to maybe mention this quickly. When I have this notation here, that is basically our velocity, our average velocity. So it's like when you're looking at 2 different time spans, or like going from one time to another. In part B, it's asking me what was the speed at t equals 3 seconds. So we want our instantaneous velocity in this situation because it's at an exact precise point. So this time I'm going to do the limit for the change of t approaching to 0 and change of d over change in t. To find the exact speed at this point when t is equal to 3 seconds. So how do we set this up? Oh boy, I have to move this because this is way too close and we need way more room than that. So we can move that and hopefully we have enough room now. If we are working with this, we want to do the limit as h approaches 0 for f of 3 plus h minus f of 3 all over our h value. So we chose this formula in this particular case because of the fact that it's right at t equals 3 seconds. It's important to know that. And then we can carry on and go through this with our calculations. Just to remind you, because I feel like we've lost it here, it was d of t equals 3t squared. So I'm going to just put that there. d of t equals 3t squared was the formula that we were originally given or that we were working with. So I'm just going to circle that so we can see it and use that to help us here. So the limit as h approaches 0, and I'm going to basically, if my time here was at 3 seconds, I'm just going to manipulate our equation to use that 3 seconds to help figure this out. So in my equation, since the overall function is 3t squared, I'm doing 3, and I'm going to do this to show you, instead of 3t squared, wherever I see a t, I am plugging in this f of 3 plus h. So I'm actually going to do 3. I don't know what the best color is to use to make this clear to you, but I'm hoping this will help you to visually be able to tell what's going on. So 3 plus h squared, and then here, notice that we had minus f of 3. So I'm going to do minus f of 3 would be 3 times 3 squared. So I'm just plugging in 3 in for t there. Okay, so then the whole thing is divided by this value of h. Okay, so I'm going to start working this way to show you what's going to go on with this. When we take this and distribute it and multiply it out, what we're saying is, I'm going to write this here so you can see, actually I'm going to make it green so you can see where it's coming from. That's just this 3 here. And then when we distribute like 3 plus h times 3 plus h, what we're going to get is 9 plus 6h plus h squared. Go ahead and do that if you need to refresh your memory, but at this point I'm going to assume most of you are pretty okay with doing that. So I'm not going to go through and FOIL all that out. And then this part here, 3 squared times 3, so I just end up getting minus 27 at the end there. And then again, the whole thing is over h. Okay, so this is just us like working our way through the algebra to simplify things. We want to distribute this in the next line. So we're going to multiply all of that out. Again, if you want, you can pause the video to do the actual work to distribute all that out, but I'm not going to go through the step-by-step process. I'm going to assume that at this point, everybody is okay with doing that. But please do pause the video and check to see if you're unsure, just that you are okay with multiplying that out and simplifying our values. I'm just going to tell you that after we go through that, we end up with 3h squared plus 18h all over h. So that's when I've distributed, collected like terms, canceled things out, and cleaned things up. We end up with this here. We know that our problem, like the problems we've been talking about for the last few days, is that in the denominator we have an h, and our limit is saying as h approaches 0. So we can't have 0 at the bottom. But luckily we can see this and notice that there's an h that can be factored out at the top. So 3h plus 18 is what I have left. And I can just pull out the h and divide it out. So that allows me to cancel this, which helps us to solve our problem, because what we're saying is if we're looking for this limit as h approaches 0, well, that means I'd plug in 0 here for this h, so it's wiped out. So after all of that work, I found that this is equal to 18. Let's go back and double check, like what was I even looking for? What was the speed of the car at t equals 3 seconds? So we just found this would be 18 meters per second if you go back and read the word problem. And it's always a good idea when we're doing word problems to put it into a sentence. So the velocity is, I should say was, the velocity was 18 meters per second at time equals 3 seconds. So after all that work, this is what our answer would be. That's what we would end up getting. So, yes, I want you to know how to punch in numbers into the formula, but you need to know what it represents. That's the purpose of the sentence at the end. It's, yeah, you know how to plug stuff into formulas, but do you know what it means? Do you know what it is you calculated? And do you know how to use the correct units? So make sure that you do that as your last step when working with this. And let's move on to this next one. So let me just, why is it not cooperating? That's okay, I'm just going to go over it. So we have, in the next example, hot gases are blown outward at 1,000 kilometers per second. How fast is the surface area growing when the radius is 8.64 times 10 to the 7 after 1 day. Okay, I don't know why I'm having issues with this thing, but I'm just going to get rid of this and we can rewrite that after. So, again, I would say at this point, pause the video, try this on your own, see how you do with it, and then hit play again when you're ready for it. But let's take a look at what's going on here. So if hot gases are blown outward, so we've got to think of what it is that we're talking about. We are looking at rate of change, but this time, so let's write this out. Our rate, because it is still a rate of change, this time it would be the change in surface area over, so how fast is the surface area growing when the radius is blah, blah, blah. So it would be over the change in radius. So in each scenario, because I'm going through a few examples with you, but this could represent a number of different things. So your job in each word problem, in each example, is to figure out in this specific example, what is my rate of change, or what does my rate of change represent? So in this case, it's sort of looking at it this way. The surface area depends on the radius. So change in surface area over the change in radius. And just a refresher, and you don't need to worry about this. If you don't quite remember this stuff, I'll tell you these formulas, but you're probably okay with this. Surface area would be 4 pi r squared. So yeah, don't worry, you should probably know that, but if you've forgotten, I'm going to give you that. And then the radius would be the tangent at 8.64 times 10 to the 7th. So when the radius is at this value. So let's take a look at how we would go through this. Again, we would do the limit as h is approaching 0, because it's precisely at a specific place, of f of a plus h minus f of a all over h. And hopefully by now this formula that we're using over and over again you're familiar and comfortable with. So we would then apply it to this specific example. So taking a look at what we're working with here, the limit as h approaches 0 for 4 pi, and instead of r, I'm going to have a plus h squared minus 4 pi a squared all over h. And I didn't color code it, but I'm going to do this time for my sanity, because the color coding takes a lot of thought. So that's representing that part. For this part, we have this here. And so hopefully that makes it super clear for you where we're getting all this from. And the formula, or what we were using to plug this into, of course, is our surface area formula there that you know from past knowledge. We're dealing with a sphere, right? Okay, so again, the rest of this from this point forward becomes all about our algebra skills and simplification skills that we've picked up and practiced over the years. So again, I'm going to assume that you are all okay with a plus h times a plus h and expanding and multiplying that out. So when you do that here, you would get a squared plus 2ah plus h squared in here. And so again, that's just representing that part. And then we have minus, and we still just have the same thing, which is 4 pi a squared, but I'll show you with this again that it's this, and the whole thing is over our value of h. And the reason that we're doing this is we want to simplify, cancel things out, and make it easier for us to work with. So after just like you would want to, distribute this to all of these. And again, I'm going to assume that you're all okay with doing that. You're just multiplying and expanding out the brackets. When you do that and start to simplify things out, you're going to hit a point where you get 8 pi HA plus 4 pi h squared all over h. You'll notice when you go and distribute and expand this out, the 4 pi a squared, they're going to cancel. So that helps you to see where this comes from. I am going to say for sure, pause the video at this point and do the expansion and the simplifying yourselves just to double check and make sure that you're good with it, because that's the part where there's so much room for error here by forgetting things, leaving something off. So don't take shortcuts. Just take the few seconds to actually do it. And then you can see here that we actually have an h here, and that's going to allow us to cancel out the bottom. When we do that, again, I'll show you this time. So if we pull out the h, we're left with 8 pi a plus 4 pi h. And then that's going to allow us to nicely cancel out the h's here, which allows us to get rid of our problem that we had, which was that h was approaching 0. So with h in the denominator, we would be stuck and wouldn't have anything that we would be able to work with. So then notice where that leaves us. We have the limit as h approaches 0. And again, looking at this here, all we're left with is 8 pi a plus 4 pi h, but notice if we have h approaching 0, that means that part's wiped out. So what does that mean? We are left with 8 pi a. And what was the a? Well, let's go back to the original question. Do you see that the a value would be this value? That's the precise point when the radius is 8.64 times 10 to the 7. So in our formula here, I'm going to write it just below here. We would have 8 pi times 8.64 times 10 to the 7. So our rate would be 2.17 billion kilometers squared per day. And that's what we would get. Okay, so you can work on page 43, numbers 1, 2ab, 3 to 8. I want you to do all of them for these. And omit number 5, meaning don't do it. Whoops, I missed part of it. There's all of your work. I hope